Something that probably should be used a lot more for visualization purposes in business. It is very commonly used in a variety of fields, particularly in the field that I work with, which is ecological data. But computer scientists are starting to use this sort of technique as well if they have non-Euclidean distances, which is I'll talk about distances in this course a bit actually, in this lecture, because it becomes important. But although I will probably be giving a lot of biological examples, because it is primarily used by biologists, the technique as a whole is very, very useful. Right? I would say, in fact, that it would give one of the main uses of PCA that we've used, right, was to visualize the data, right, to get a 2D representation of our high-dimensional data system. The problem was, of course, is that it is a projection method. So if you have let's say here's our first PC here, and the second PC is there. If you've got data points that are sitting on these axes, they're going to get projected down to the same point, okay? And they're not going to look very different on our map. And that's just, the information that's being lost. So the PCA will work really well if we've got really nice and normal data, and there's a lot of variation that's explained by the first two axes. Otherwise, the actual map is not so ideal. In fact, we can get a better map probably using this technique called multidimensional scaling. Right. So multidimensional scaling is not a nice, neat algorithmic. It is an algorithmic method. It's not a nice, neat analytical method of getting a projection and analyzing it. Conceptually, it's much simpler than that, but it does have this flexibility, and that is that you can calculate it using lots of different types of distances, right? And as a consequence, we can actually start fitting in binary variables. Will fit in quite nicely into our technique if we want to. So what we've calculated so far, when we think of a distance, the distance that you and I live in the real world, is what we call Euclidean distance, right? It is the straight line distance that we use using Pythagoras' theorem, right? So if I have two objects, here's object 1, and that's sitting at the coordinate system 1, 1, and object 2 is sitting at 5, 4, right? Well, what's the distance between this? Well, what do? We use Pythagoras' theorem to calculate this distance of 4 and this distance here of 3, and then we square them both and add them up and square root it, right? A squared plus b squared equals c squared. Remember that? It was like when you were about 12, I think you would have done Pythagoras' theorem. So that is simply the distance. But it is, of course, you can carry on with this. This is just 2 dimensions, but you can carry on with this in 15 dimensions. You can calculate the distance in a 3-dimensional space. You do exactly the same thing. You add up all the individual distances, you square them, and then you square root the final sum. So Pythagoras' theorem, of course, is not restricted just to 2 dimensions, is my point. Right? So this is the Pythagorean theorem, which is not difficult to most of you guys. So what is that? That is simply that this is just saying, hey, what's the distance between object 1 and object 2? Well, it's just calculate the distance along axis 1, right? So this is axis 1, or variable 1. Do the same thing for variable 2, right? That's the distance between the objects. You're squaring them, and you're adding them all up. So if you've got another variable, you just add that one onto that as well, that distance squared, and then you square root the final thing. Right. So obviously, in this case, it's going to be pretty trivial, right? But it turns out that in a lot of situations, particularly for biologists, but also true for other scenarios, you might want to consider other types of distances. You might have data that has lots of zeros, or for some reason, the zeros actually signify a lack of information. You might have data that are heavily skewed. You know what I mean by skewness, right, you guys? If you have a heavily skewed distribution, then rather than being symmetrical, the tail of the distribution heads off into one direction or another. But perhaps you've got non-quantitative data, binary data, or ordinal data, right? This is what statisticians typically call data that are misbehaving. Right? Because we like our nice normal distribution because all our statistical theory is based on that, right? Right, so in these cases, sometimes it makes sense to base your map, your ordination, on something other than a Euclidean distance. And I'll give you a particular example that's relevant to biologists, in due course I will. So what we're going to do is we're going to describe something called a measure of resemblance, how two objects resemble one another, how similar they are with one another. Right? So this is going to be, I'm going to talk about measures of resemblance, and these are just measurements calculated between two things, like there's two objects, right, on the basis of a suite of variables. So just as like we have done with the Pythagorean theorem, we can look at how similar two objects are, right? So in essence, this is analogous. I'm going to expand my definition of distance to talk about other non-Euclidean distances, or alternatively, the flip side of that coin is not how far apart they are, but how close together they are, how much they resemble one another. So this is going to simply be a reflection about how much these two objects are similar to one another, or conversely, how different they are to one another, right? So this term, the measure of resemblance, sometimes they're called a measure of association, sometimes it's called a coefficient of resemblance or an index of resemblance. Typically, they're called distance measures or measures of dissimilarity. Right? Depends on the context. It depends mainly on the field of study that you're doing, or that you're working in. Okay, so let's deal with binary data. Right? We want to compare two objects, and we've simply got binary data. Right? So here's object 1. This might be customer 1, and this might be customer 2, and this might be whether or not they've bought product 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So customer 1, object 1 has bought, both customer 1 and customer 2 have bought product 1. Only customer 1 has bought product 2. Neither of them have bought product 3, and so on and so forth, right? So here we have different variables, and we can think of those as different products, or if you're a biologist, as different species, perhaps, right? And these are our observations in the rows. And what are we trying to do? We're trying to characterize how similar object 1 is to object 2, right? Because I want to be able to map them. And if they're very similar, I want to map them so that they are close together. That makes sense, right? Yeah. Okay, so I can summarize this table using a confusion matrix, right? And that is basically the times they are both similar, it's going to be in this diagonal, and the times that they are different, here, this is for binary data, right? So we've got A, B, C, D. I'm going to use these terms A, B, C, D. A refers to the occasions when both of the objects had a 1 in it. D is going to be when both objects, both cases, but say both customers, have a 0 for that particular variable. We're simply going to count them. And B and C are when they are different, right? So B is when object 1 didn't have it, but object 2 did have it. And C is the other way around, when object 1 did have it, and object 2 didn't have it. Okay? So you can see these are when they are similar, right? And these are when they are different, the two objects. B and C are measures of, somehow measures of differences between them. Right, so A is going to be the number of characters, the number of variables that are shared by the two objects. Right? B and C, as I've stated, are when they are different. But what we're doing is we're counting basically the columns. A is the number of columns where they're both 1. D is going to be the number of columns when they're both 0, I should say, right? The number of characters possessed by neither object. And B and C refer to the number of columns where they're different in one aspect or the other aspect, right? 0, 1 versus 1, 0. Does that make sense? Any questions? Okay, so let's have a look at this particular data set then. Right, so what is A for this particular data set? 2, right? How many times did we get a 1 and a 1? There and there. Right? How about B? B is also equal to 2. That's when we got 1, 0 occurring. 0 and a 1 occurring. C is going to be the other way around. That's a 1, 0. So that'll be 3, hopefully. And D is the times we got 0, 0. Here and here. Right? Okay. So if you think of one measure of how similar these objects are, would be to see, well, okay, given we've got 9 different variables, how many times did they match up? Right? Well, they matched up here, they matched up here, they matched up here, and they matched up there. Right? Out of how many? Well, there were nine variables. That's what your simple matching coefficient is. The times they were similar, A and D, versus all of the columns, A, B, C, D. Right? So the sum of A, B, C, D is, of course, just the number of variables you're looking at, right? So that's the times they got it right. Another way of looking at it is the proportion of variables that they were similar for these binary variables. Yeah. So this is very commonly used. Probably it's nice and intuitive, right? But, and this is particularly important for biologists, but it's also relevant probably for other fields of study. What happens with double zeros? Are they actually important? Do we want to consider 2 objects to be more similar just because they both happen to lack particular characters? Right? So we are actually saying, hey, they're important because of D, the times that they got 0, 0. I could arbitrarily add extra variables in there, right, that they both happen to lack, and then these objects would become more and more similar as a consequence. Right? So in some respects, that doesn't really make sense. A lot of times it does. If you are actually interested in the times there are double zeros, then absolutely, then D would be useful as a measure of similarity. But a lot of times, we're not interested in that, right? As a biologist, I'm particularly not going to be interested in that. Right? So often, I would say, like most ecologists, I would say, I don't want the double zeros to contribute to how similar my 2 different objects, my 2 different sites are, right? I don't want to say, hey, look, estuary 1 and estuary 2 in Auckland are actually a little bit more, are a bit similar because neither of them have polar bears in them, right? Neither of them have lions and tigers in them, right? I can go through the list of animals and make them appear to be very, very similar because they both lack all of these different animals, right? It doesn't actually make a lot of intuitive sense to do that, typically. Right? So 2 assemblages of trees should not be considered more alike simply because they both lack elephants, for example. Or in my case, because I study, I'm a marine biologist, I often have studied shellfish assemblages. When I say the word assemblage, I mean a group of animals coexisting together, basically. I don't want my shoreline assemblages to be considered more similar to very deep assemblages because they both lack the mid-pelagic species, the animals that live in the middle of the water. But you see my logic, right, about the problem with double zeros and how perhaps you don't want that to be measured when you're describing similarity. Right? So the double zero problem is sometimes called the joint absences problem, right? It's absent for both of the, I'm comparing 2 different customers, right? If we've got a 0 and a 0, it's absent for that variable, but it's a joint absence. Right? So the decision of whether or not to include these joint absence information depends on the context, because sometimes it is going to be useful to us. Right? So does the 0 mean an absence of information, or does it actually mean really mean 0? The characteristic is really not there. Right? If it's the latter, then maybe we actually have some useful information in that joint zeros. Right? But if in fact it's just another characteristic that is not particularly useful, then maybe you should be discarding it. So how do we fix that? Well, Jacquard's similarity just does away with it. in the denominator, right? It simply calculates the number of joint ones compared to all of the data, but it doesn't include the joint zeros in my denominator. Right? So I just pretend that they weren't there, those columns weren't there. Right? So this is equivalent to A divided by A plus B plus C. But you notice that D is not in here now. Right? Those joint zeros have been discarded. So let me show you. What would be, we know what the simple matching value was here, right? It was A plus D divided by 9, right? Here we're going to calculate, basically, we're going to ignore D. And so how are they similar? Well, they're similar to A. How many items are there that we're going to consider? Well, instead of 9, we're just going to ignore this one and say that there were only 7 items. Right? So the S sub j is going to be the similarity according to Jacquard's similarity, right? S sub j is 2 divided by 7.286. Right? So if we're ignoring joint absences, these two objects are just 28.6% similar, right? They share, for example, about just under 30% of the variables of their binary variables. 2 out of the 7 characteristics. Whereas if I was to use the standard simple matching, I would consider all 9 variables, and now all of a sudden the objects seem to be more similar, about 44% similar, right? They should be mapped slightly closer together, in other words, in my map. So you follow this logic, right? You guys, don't be afraid to ask. That's a very funky pen position. Okay. So these measures of similarity are very common if you've got lots of binary variables, right? And you can describe them as, hey, look, simple matching is nice and easy, or as is Jacquard's to describe. Look, these two objects are X% similar in their composition, right? According to presence-absence data. And there's more and more variables that are presence-absence nowadays. A lot of data, it's very, very common to get 0-1 data, binary data. So there are lots and lots of different distance measures or dissimilarity measures, right? Some of them include double zeros, Sokal and Sneath, Rogers and Pearson's 5, there's a whole bunch of them, right? And there are a whole bunch of them that exclude double zeros. Sorensen's coefficient, Kolchinsky's, OKI, Faith, I use something called Bray-Curtis, that excludes it as well. That's what most ecologists use. So we're not going to worry about that, right? In data mining, I'll teach you something about the cosine similarity. That's used for text mining, right? That tends to, I think that basically excludes zeros in its calculations. Okay, so now we've got this idea of what we can do with binary data, how we can calculate that when we're using a distance measure, right? So we can include binary data in our measure of similarity of some sort. So we want to now do what we did before, like with a PCA. We want to construct an ordination. What do I mean by that? It means I want to make a map of our data points. I'm going to say in Euclidean space, because it's just going to be a map, and any map is in Euclidean space, right? Because that's what we see things. So that if 2 points are close together in Euclidean space, right, on the map, then they are considered close by us, looking at it, right? So we want to construct a map, basically, using information just given by the distances or the dissimilarities amongst those points. Right? So this is the big difference now between PCA, well, one of the main differences between PCA and NDS. PCA was actually using the coordinates themselves, the actual coordinates. Now, we're going to create something using a map just using the distances. Just using the distances, right? So we've got our data, and that's n by p, right? There are n rows and p different variables. From that, we're going to calculate, well, okay, here's the first row and the second row. What's the distance, or the dissimilarity between the first and the second object? That's going to go in here, then do the first and the third, first and the fourth, and so on and so forth. In the end, we end up with an n by n matrix. Every object is considered against every other object, right? But of course, going from 1 to 2 is the same thing as looking at the distance between 2 and 1. So actually, we can just look at 1/2 of this data. Right? So the distance between the first customer and the second customer is the same as the distance between the second customer and the first customer. That's just the flip side of it, right? So these two are, there's still a symmetrical matrix and it's a mirror image. Right? So we've gone from a rectangular matrix to a square matrix. Right? So we're going to be using this distance matrix. And this is used in Felix, yes?
May I ask that, is that means the MDS just works for the binary matrix?
No, not at all.
So
So that was just a way of calculating binary data within it, right? We can calculate it using Euclidean distances as well for continuous variables, right? So yeah, we will probably use Euclidean distances in this instance here.
Oh.
Okay, so we're going to use, mainly we're going to use our data are going to be, our examples will be actually real variables, and we can just calculate the Euclidean distance for them, right? But we can, if we want to, calculate dummy variables for nominal variables, and also calculate a coefficient or a distance, include a distance that that incorporates those binary variables if we want to. Right? We're not going to do that in the course. We're not going to use both quantitative and qualitative variables, but it can be done, right, in that way. Okay, anyway, the point is that we can actually choose a distance of our choice. So let's say we were ecologists, right, and we had 3 different sites and 3 different variables, or 3 different species, right? Alternatively, you could consider this to be 3 different customers and with 3 different products. Products would be the columns, right? And you can say, well, how many I don't know, products do they buy of each of these things? And you want to see how similar the customers are, right? If we were to calculate the Euclidean distance, so just to directly answer Felix's question, of this, well, okay, what is the distance between 1 and 1? It's always going to be 0. So the diagonal and 2 and 2 is 0, because these things are exactly the same, right? So they are, there's no distance between them. They are perfectly similar, right? So the dissimilarity is 0. So the distance between them is 0 on the diagonal. That's the standard. What is the distance between site 1 and site 2? Well, it's going to be the difference between these guys squared plus the difference between these guys squared plus the difference between these numbers squared, all added up and square rooted. So basically the square root of 3, right? Because that's 1, 1, 1. Square root of 3 is 1.73. What's the difference between 1 and 3? Well, that's not going to add anything to it. That is going to add something to it, right? And likewise here. Right? So that would be 3 squared plus 2 squared, all square rooted, 3.61, and so on and so forth. So you can see how, and then we can do the same thing for between 2 and 3, right? So you can see that we are comparing every customer with every other customer, right? So that leaves us with quite a lot of values in here. Obviously we've got 0 down the diagonal, but we've got approximately n squared over 2, approximately other distances that are calculated. Of course, you're not going to be doing this by hand. The computer can do it very quickly. And you can check the math if you like it yourself. Hopefully it'll work out, right? So hopefully this should be what? Between 2 and 3? 1 squared plus 4 squared plus 3 squared. What's that? 4 squared, 16. 3 squared is 9. 25. 26, root 26, 5.1. Well, that'll be right, because we know 5 squared is 25, plus a little bit more. You need a calculator, really, right? Everybody knows the square root of 26. Phew, got it right. Okay. So, as I've denoted, this is a triangle, a symmetric matrix. So the upper data, I've left it blank here, but of course these are actually the same values. But just to make it easy to view, people just usually show one half of the triangle, one half of the data set. Okay, any questions? So we've gone, I took a quick aside to show you how you can work with binary data, and now we're back to continuous data again. Right? We're not going to worry about that. Okay, so the distance matrix, I'm going to call that D. It is symmetric, as I've just stated, which means the transpose of D is the same thing as D. I can flip it around, the rows and the columns. The distance from object 1 to object 2, from customer 1 to customer 2, is typically the same as it is from 2 to 1. So that's this idea of symmetry, right? Typically it's symmetric is what I should say. The distance matrix has zeros along the diagonal, right? Which means the distance between any object and itself should be 0, which makes sense, right? They're identical to one another. So this is actually the starting point for a number of multivariate methods, especially non-parametric ones, most of which you won't learn. The two that you will learn is going to be MDS and cluster analysis. Right? So this idea is going to be useful for cluster analysis as well, this idea of a distance matrix. So what we get basically is pairwise, it's filled in with pairwise similarities or dissimilarities. So we can work with, we can calculate distances, or we can calculate, conversely, we can talk about how similar objects are. And if that's the case, we're going to have ones along the diagonal because, you know, rather than having a distance of 0, they're basically saying, hey, look, these things are identical. They're very similar. So object 1 and object 1 have a similarity of 1. And typically, since the distance, so often we have, if we're dealing with binary data, we have a range of values between 0 and 1. Distances are bound between that. So the converse, 1 minus that, talks about similarity. Okay, so here's the idea. Yes, Jamie?
If using the Jacob, because you're ignoring the double zeros,
Yes.
but each of those pairs might have a different sort of double zeros, so you can pick that on a different range of factors.
That's right, yes.
And that's
Yeah,
right.
that's right. But it's still bound by, it still has the logical interpretation of, hey, look, of those objects that have information in it. You know, how similar are these particular cases? So, I didn't quite state that very clearly. Of these two cases, you know, what proportion of objects are similar, given that they have some sort of information in them? Right. So yes, the denominator is changing, but the value is still going to be bound between 0 and 1, right? Because you can never get the numerator bigger than the denominator. You're just throwing away from both of them. Right? So it still has a logical interpretation, despite the fact that the denominator does vary between these things. That's a good question. Okay, so let's get to the idea of MBS. So, if I was to measure all these variables, right, basically we've got this very high dimensional space. Right? If I have, I don't know, 4 different variables, and I want to calculate the Euclidean distance between, or the Euclidean similarity of objects in this 4-dimensional space, I'm going to, you know, I have to work in all 4 dimensions, right? But I want to just be able to map this to some sort of lower dimensional space. So what I want to do is basically calculate, have something. So let's say we've got, I don't know, our data is sitting in 3-dimensional space, right? And we have 2 objects sitting in this 3-dimensional space here. We want to ensure that the Euclidean distance that we get on the map represents the full dimensional space very well. Right? Ideally, let's say that full dimensional distance was, I don't know, 3. Then we want to ensure that this is 3 units apart as well. Okay? And because we're going to be calculating, you know, with a bunch of objects, you get a whole bunch of distances, you can see how they're going to be constrained very quickly where they could potentially go. So here's the rationale. We choose our distance measure of choice. Typically it's going to be, for you guys, it's going to be Euclidean. Typically for an ecologist, it's going to be something completely different like Bray-Curtis. We're not concerned with the original variables per se, right? We're not going to use the Y matrix. Instead, we're actually going to calculate this, this MBS using the distances amongst the points. Sometimes it's the only data that we have, in fact. You don't actually have the original data, you only have distances, how similar objects are. Right? And we can conversely work with similarities. You come up with the same result. You can also apply this to correlational data. Correlational data does have a problem with it, however, that I'll talk about. And what's our objective? We want to produce a map in two-dimensional space, right, if it's on a piece of paper, or sometimes three-dimensional space, but usually just a map on paper in 2D. So this is a Euclidean map that represents the configuration of distances that we see in the higher dimensional space. Right? So the points in the high dimensional space that are far apart are represented on our map as being far apart. Right? Does that make sense? Points that are similar to one another should be close to one another on our map. How the hell do you do that mathematically? The answer is you don't really. It's iterative. You throw the points down and you start moving them using gradient descent until it actually matches up as close as you can get, and that's the answer. Okay, so choose the number of dimensions that you want for the configuration. That's going to probably be 2, isn't it? Because you want to produce this on a piece of paper that you can print out and give to your boss, or print out and put on the web. Sometimes it'll be 3, but then you have to have the rotational aspect of things, right? So you want to place the points into that two-dimensional space such that the Euclidean distances on the reduced space, on the map that you're drawing, replicate the actual dissimilarities as well as you can. Right? Points that are really far apart, I'm going to reiterate this, points that are really far apart in the full dimensional space should be drawn far apart on the map. Points that are similar to one another should be very close to one another on the map. So there are 2 ways of doing this. And you might be dubious of the second way, but it's probably the most common way. That's called non-metric MDS. Non-metric MDS doesn't even use the distances. It simply ranks the distances, and then just tries to replicate the ranks. You would be very surprised at how well this works. So metric MDS versus non-metric MDS. Okay, so these are basically, the objective is the same for both of these things. It's just going to be a subtle difference in the loss function, essentially. Metric MDS, essentially, we have this relationship between the new Euclidean distances, between the map distances and the original high-dimensional distances. We're going to say that's linear. We want to try and recreate it. So, hey, look, in the full-dimensional space, let's say the distance is 4 between these 2 points, and here's another point here, and that point is 2 and 2 there. Well, we're going to put it on the map so that whatever it is that we choose, the positions that we choose for these points, is going to have a linear relationship. So obviously, the first 2 points are twice as far as the other 2, so we want to put that third point perhaps in the middle, right? And it doesn't matter if I could blow it up or shrink it down as long as it is proportionately in the middle. Right? So that means that there's some sort of linear relationship going on between the map distances and the original full dimensional distances. Right? Non-metric MDS, in fact, doesn't deal with the distances at all. It simply actually does, the relationship it's looking for is some sort of monotonic relationship between the full distances and the Euclidean distances on the map. Right? So in fact, the only thing that you're trying to preserve is the rank of the distances. So if you know, hey, look, this one, let's say we've got 3 distances, right, and 3 points. This one is the most distant to one another. So I want to make sure that on the map that I draw, this one is the most distant to one another. That's the only thing that I'm actually looking at. I'm not actually looking at the actual distance, just the rank of them. These 2 points might be the most similar to one another, so they will be drawn the closest together on the map. And it seems unbelievable that you've thrown away a lot of information, right? All about what the actual distances are. All you've got are the ranks of the distances. But you'll be surprised if you have a few data points how quickly this will resolve to a very accurate map of reality. So we're going to focus on this version, right? It's only relatively recently, I think, that people have been using metric MDS with some success because there are some nuances here that that make things that they're only starting to realize. Most people use non-metric MBS simply because it is robust. It gives a good map, right? It's robust to outliers, and it works quite simply. It tends to work very well. So what are we doing in non-metric MBS? We're considering the actual values to be somewhat arbitrary. The only thing that is of interest to us is the ranks of the distances. In other words, the relative differences. Right? So I'm basically ranking which objects, which distances are the most distant to one another, from 1 to the closest pair of points to the least close pair of points. And we're going to construct a map based on that. Right? That's going to try and imitate the high-dimensional map. So once again, the goal is to order the points on our map relative to one another. In this instance, it's going to be in the same order as the original dissimilarities in the full dimensional space. So we want to do this as well as we can in our two-dimensional space, right? Typically a two-dimensional space. So unlike a PCA, so in a PCA, you run your PCA, and you can, from that single PCA, you can say, okay, I'm interested in creating a two-dimensional map. Here is PC1 and PC2. That's my best representation. Oh, actually, maybe I'll do a three-dimensional map. So I'll just add PC3 in there as well. And then I can look at the points sitting in the three-dimensional space defined by my PC1, PC2, PC3 basis, right? With an MBS, you have to choose the number of dimensions beforehand. Because you'll get a different configuration of points if you choose, let's find the best two-dimensional representation that we get, and then, let's do a three-dimensional representation of points, right? The two-dimensional representation doesn't just get changed. You have to do the entire algorithm again, right? So you have to actually decide, well, what dimensionality am I going to view the data in beforehand? This is not a big constraint, because nearly always the answer is 2. Anyway, right? Just as it is with PCA. Okay, so we use something called the Shepard-Kruskal's algorithm here. So what are we trying to do? First step is to rank the distances in the distance matrix from those points that are most similar to the points that are furthest apart, right? So we've got a bunch of distances here, right? Which one is the smallest? Which one is the biggest? We're just going to replace the actual values with a 1, 2, 3, 4, 5, 6, 7, just the ranks, basically. Right? And we're going to say that these ranks are basically monotonically related to the actual distances in the full dimensional space. So we're going to say, hey, look, in this map that we've got, if in fact the distance between R and S is less than the distance between U and V in the full dimensional space, we want that to show. We're going to say that hopefully the ranks are going to show that as well. The ranked distance between R and S is going to be less than the ranked distance between U and V as well. Right? Hopefully we're going to be able to do this. Right? So in the original distance, here we've got the distance between A and B is less than the distance between C and D. Hopefully that will be reflected in our ranked distances as well. Achieve or in the distance that we get on the map, basically. Okay, so the third step is we're going to find a configuration of points, right? And those points will then have their own interpoint distances, right? So we've got our full dimensional space, and we have a whole bunch of points, right? And we're going to use the ranked distances between those, and then we're going to draw it on the map. We haven't said how we're going to draw it on the map. We're just going to put our configuration of points, and we're going to calculate those distances between those, right? So point A in the full dimensional space will have a representation on the map as well, right? So will point B. Now, and if A and B are far apart in the full dimensional space, hopefully they will be far apart on the map, right? But I haven't said how we're going to mess with that. Well, I have. Okay, so the first thing you do typically is actually, and this seems unbelievable, is you just put the points down at random on the map. right? Completely random. So at this point in time, the distances on the map don't reflect the ranked distances in the full dimensional space at all, right? Sometimes, and this